So, how do you build these complex communication satellites? The production of, let's say, a car starts with a sheet of steel. And in case of a satellite, it is this sort of carbon material. It feels soft, but it will later become a stiff spacecraft skeleton. The idea behind carbon plastic is using carbon fibers into weaving a carbon fiber fabric. The fiber is submerged in a binding solution. Usually it's epoxy resin. The material is later shaped with the help of a knife and a matrix. Then we let it dry, and voila, here's a part of a future satellite. The weight of the carbon fiber parts, of course, is extremely important. This is a future satellite antenna pole, an extremely sturdy thing. It's 6 meters long. You can lift it with your left hand. Actually, a finger of your left hand will do the job. The assembly of a communication satellite starts at the milling center. We start with the carbon fiber primary structure. Then we attach honeycomb panels. Here's our future body frame. To an amateur, it may seem, well, what kind of a frame is this? Must be a joke. Foil cells. It's wobbling. What sturdiness or stiffness are you talking about? The key here is the top and the bottom of the cellular foil, it is called the honeycomb core by the way, is reinforced with aluminum or plastic plates. The core turns into a stiff frame after it dries. Very stiff and very light, same principle as in carbon plastic. The future spacecraft parts must be both durable and light. Why is it so important to cut weight? Any satellite consists of 2 big parts, a service module and a payload module. Service systems consist of engines, batteries, solar panels, whatever is required for in-orbit operations. The payload is the reason the satellite is in orbit. The tools, for example, communication satellites need antennas and transponders. Therefore, the lower the spacecraft weight, the more payload it can carry. There is a direct correlation between the two. As in any other electronic device, be it a phone or a tablet, satellite microchips in satellites tend to get smaller each year. Microchips are assembled into blocks. They are then attached to the frame. The communication satellite literally snowballs into what it's meant to be by adding new units and parts. In general, the spacecraft assembly has very little to do with assembling, let's say, a car. Too many fundamentally different systems. That is, solar panels are built by one manufacturer, antennas by a completely different one. And often, the service module and the payload module have different manufacturers as well. But manufacturing is one thing, assembling and testing is another. Here's the reason why. Communication satellites will have to function in space for 5, 10, 15 years. And if something goes wrong, we can't just send over a maintenance team. There's no such thing as maintenance for a satellite. Therefore, we have to double-check each unit and block to make sure they are durable, among other things. Electrical testing is perhaps the most common test for any satellite, including communication ones. But in between electrical tests, a spacecraft undergoes a number of exotic durability tests. This construction is called a thermal vacuum chamber. During the test, the chamber is sealed, air is removed, creating a high vacuum inside. And then the temperature is alternated between plus 150 degrees Celsius and minus 150 degrees Celsius, thus creating conditions most closely resembling outer space. That is how experts test whether a communication satellite and its blocks can endure extreme temperature changes while in orbit. And in the next room, they test if the satellite can make it to the orbit. This is a vibration and transportation loads testing stand. Here we recreate the shaking conditions the satellites will undergo, first and foremost on their way to the launching site, and later during the rocket launch. And this is an acoustic chamber. Here, the spacecraft will literally get deafened. The communication satellite is almost ready. There's one more important test, antenna testing. They are tested in an anechoic chamber. The signals here are not reflected back from the walls. Everyone leaves the room during the test. Too much radiation. If all goes well, the antennas will get locked down. They won't be moving until they are in orbit. One of the final stages of a satellite assembly is wing attach fittings. The wings consist of solar panels. Well, then there's only one thing left to do: transport it to the launching site. Spacecrafts are transported in special containers. They serve both as protection and microclimate chambers, maintaining certain temperature and pressure to avoid dust penetration into the satellite. By the way, almost every spacecraft has a name. Gazprom's communication satellites are traditionally called YAMALs. Now, we're motorcading to the airport, where we will catch a plane to Baikonur. Yamal 401 communication satellite is delivered by an AN-124 to the launching site. Simultaneously, the Proton M launch vehicle arrives there from the Khrushchev Center. Now, these two fundamentally different systems need to be joined into one. That's the building for this task, the assembly and testing facility. These facilities are a part of almost every spaceport. Otherwise, it is impossible to assemble and test the launch vehicle, and most importantly, to mate it with its head, the satellite. If the communication satellite arrives here in just one container, it takes 16 cargo cars to transfer the Proton M launch vehicle. Now we can start assembling the rocket. The assembly of the rocket reminds one of a construction set. The first stage is assembled on this jig. Then the first stage is transferred by a crane to that part of the facility and mated with the second stage, then the third stage. This is schematically depicted in reality, however it takes a while to finish. The Proton has already been fully assembled and tested at the factory. Nevertheless, it undergoes a series of tests here as well. The Proton is a heavy lift launch vehicle, meaning it is more powerful than, say, a middle-class rocket, Soyuz. Therefore, it can bring heavier cargo into orbit. Proton rockets are 3- or 4-stage-to-orbit systems. The fourth stage of the spacecraft is a booster. And as a rule, these rockets are used to launch geostationary communication satellites, the largest and the heaviest satellites of them all. The communication satellite is assembled and tested again on a separate jig. Now it's time to install the Yamal 401 to the rocket. The procedure is the following. This jig locks the upper stage in an upright position. Then, the crane lowers the satellite into the upper stage. Now, they are joined, then inspected. Afterwards, the first half of the nose cone rolls next to it, and the upper stage, along with the satellite, are lowered horizontally inside it. The structure is later sealed by the second half of the nose cone. And it's done. We're not nearly finished. The upper stage, together with the satellite, are later mated with the rocket. And so the LN launch vehicle is transformed into a space mission vehicle. Now we're on our way to the launching pad. Proton is moving at a speed of 5 kilometers per hour or less. And from here, it's still a 5-day countdown to the launch. Baikonur is not only the first, but also the world's largest spaceport. Its area is 6,717 square kilometers. This is 3 times the area of Moscow within the Ring Road. There are about 60 launch pads, both operational and unused. They are scattered at a considerable distance from each other due to the safety regulations. Therefore, it takes more than an hour for Proton and the communication satellite to get to the launching site. Proton is brought to the launching pad. It is detached from the rail transporter and placed in a vertical position. One would think the rocket is finally here, positioned vertically and fueled. And now, it can launch. But no, it's not over yet. The mobile service tower is rolled up to the Proton. It literally embraces the rocket. There are still a few days left to launch. Fueling the rocket takes place on the 4th day. Oxidizer goes first, then fuel. The first stage, the second, the third, except the upper stage, because it has already been fueled. The launch usually takes place on the 5th day after the rocket has been installed to the launch pad. Now the question, will it launch during day or night? The takeoff of Proton M with the communication satellite Yamal 401 has been scheduled for early morning. So we have about 2 minutes left. We watch the launch at a distance of several kilometers, again, as required by the safety regulations. Even people who launch the rocket have to leave the launching pad for safety. As a rule, they go to underground vaults right before takeoff. 1 minute to takeoff. The distance from here to the launching pad is about 2 kilometers, so the sound of the running engines comes with a delay. There it is. While watching the rocket launch or even stage separation, no one seems to wonder how exactly the satellite reaches the orbit. It seems that everything is simple. It hits the desired height, but no, only when all the stages of the launch vehicle have burned out does the most exciting part begin. 3 stages of Proton push the satellite into the low or geosynchronous orbits. Then the upper stage starts functioning. It activates 4 times. Each time, the satellite accelerates to a new height and also changes direction. This is why the upper stage is also called the booster. Its job is far more complex than those of rocket stages. It takes 9 hours for the communications satellite to reach the target altitude, 35,786 kilometers above sea level, or geostationary orbit. And now is the most exciting part. Geostationary orbit. Here, satellites move at a speed of our planet's rotation, which makes them ideal signal repeaters. Just point an antenna at a specific spot in the sky, and there it is, constant reception. This, however, does not mean that there's no need to monitor the spacecraft's progress once it enters the orbit. Despite popular belief, voila, geostationary satellites aren't suspended perfectly relative to the Earth. There are many factors that influence them. For example, Earth's gravity, solar wind, the gravity of the moon. Each of them is trying to push the satellite out of orbit. Therefore, not only is the flight being supervised, but also thoroughly controlled. Control is being carried out by satellite operators, such as, for example, Gazprom Space Systems. Here, experts monitor geostationary satellite movements, correct their orbit if need be, literally by turning on their engines to maintain them in their orbital positions. And finally, operators offer provider services. Now, let's see how the system works as a whole. Radio signals are transmitted from the satellite communication Earth stations, like the one you've just seen. The satellite in geostationary orbit receives these signals and enhances them and re-emits them back to Earth. This emission, however, now covers a huge territory. This is what we call coverage area. Users can receive a radio signal with smaller diameter satellite dishes, but what are those radio signals? Oh, these are all sorts of different information. Telephone. Today you can call someone, anyone, on any continent if their cell phones are within network coverage. You can also contact them directly by means of satellite phones. Internet. Thanks to communication satellites, it has become a truly global network. Data transmission. For example, tracing the nationwide unified gas supply system data in real time. And finally, television. Live broadcast from anywhere. Even the film you are watching right now has also been broadcast by means of a communication satellite. This is probably the main mission of these spacecrafts. Satellites make things easier and our world more accessible. Even though each of us uses these services every day, we hardly ever think about the tremendous amount of work invested in this enterprise to make all of this possible.